All right. So, good morning, everybody. Well, thanks again for coming to this lecture. Today's presenter is Dr. Eric Stach. And remember, if you have any questions, please write them in the Q&A section, and we will answer them after the break. Dr. Eric Stach, it's all you.
Great. Welcome this morning, day before Thanksgiving. So my name is Eric Stach. I'm going to give you a discussion today about transmission electron microscopy. Interestingly, I'm actually teaching this same class here at the University of Pennsylvania this semester. And so I've been sitting in on all of the lectures given prior. So I have a pretty good context for all the things you've been hearing. I'll try to draw parallels as I go. I used to work at Brookhaven National Laboratory up until 2017 at the Center for Functional Nanomaterials, which is right next to NSLS2. And that's kind of why I'm the lecturer, even though I don't work at Brookhaven. And I moved down here to Penn in 2017. So my goal today is to talk about the transmission electron microscope, how it works, the sorts of data that you can obtain from it, and also to put it in the context of how it's a tool that's very useful for materials characterization, and in specific in ways that are different and complementary to the capabilities you've been learning at NSLS2. And so I need to advance to my next slide. There we go. So I think one of the most important things to understand right at the beginning is that electrons are not X-rays, and it's useful to think about their properties because those properties have a real impact upon how we utilize the electrons to do useful things. So first of all, I mean, X-rays, as we've learned, are photons. They are, something that is a carrier of, a light, a photon energy. Electrons, however, are small charged particles. And this is a very fundamentally different thing. X-rays and electrons have a different relative interaction with the material. As you learned, right, when the X-ray comes in to see a nucleus, right, in an electron cloud, it causes an oscillation, which then propagates the X-ray forward out of the nucleus and the electron cloud of a single atom. In the case of electrons, they're small charged particles, and as they come towards the atomic core, they can bounce off of the atomic core, or they can bounce off of the electron shells, but in particular, that just changes their trajectory. And so it's something that's actually much more likely to occur in terms of the strength of scatter than an X-ray interaction with an atom. So as a result, the electrons interact very strongly with materials. And this is again because they're small negatively charged particles. They directly scatter off of either the nucleus or the electron cloud. In the case of X-rays, you're having an electromagnetic wave which undergoes a field exchange with the electron cloud. And then, of course, we haven't talked about it in this class. You're not having any lectures on neutron scattering, but they're another tool that people use to characterize materials. And in the case of neutrons, you're using a heavy uncharged particle which scatters by a direct interaction with the nucleus. So these three different types of scattering mechanisms lead to different mean free paths. A mean free path is the relative amount of a material that you will go through before you expect to have one single interaction event. So there, if you look at an electron, you have 10 to the 2 angstroms, so 100 angstroms or 10 nanometers. That means that within 10 nanometers of having the electron enter the material, you will likely see a scattering event. If you look at X-rays, that's more like 10 to the 4th angstroms, so about a micron, and neutrons 10 to the 8th, so you're looking at 1 millimeter or more. So that's a very important difference. It tells you something about how you have to think about making samples and also the sampling area that you have. Now, another big difference between neutrons, X-rays, and electrons is because electrons have a negatively charged, they have a negative charge, pardon me, you can use electromagnetic lenses to focus them. In prior lectures from Mingyuan Ge, for example, right, and Xiaojing, they gave you discussions about how you can do focusing of X-rays with either zone plates or multi-layer Lowry's lenses. Those are very complex methods for focusing X-rays, and they give you kind of a fixed focal length. In the case of electrons, you can use electromagnetic lenses, and you can very readily vary the strength of the lens which gives you a difference in the focal distance. And that's really something that allows electrons to be manipulated much more readily. A primary end result of that is that with electrons in a good modern day electron microscope, it's straightforward to get to a 1 angstrom probe size or better. The instrument I happen to have across the hallway here and down in the basement gets to 0.63 angstroms on a good day. And that's really, really small. And that's the size of an atom. And so a key difference between electrons in the use of materials characterization and X-rays and neutrons is the ability to do routine atomic scale imaging and routine atomic scale chemical characterization. So this is a real strength. So that's an important part. I've talked quite a while just to make sure that we see that right at the beginning. Electrons, because of their primary properties, are different than X-rays. It gives them unique capabilities for focusing and thus for characterization. However, they interact strongly with the material, so you have to have a lot of thought about how you make a thin enough sample to get the information that you need. Okay, so that's again, the main part right at the beginning. So what we do as a result of being able to focus the electrons is we build a rather complex microscope. This complex microscope allows us to take advantage of lenses to really nicely control how the electrons come into the sample, either as a broad range of electrons that sample a large area, or as a focused probe that allows us to do angstrom scale imaging. We also have another series of lenses that allow us to change the outcomes of what we see with respect to the electron specimen interaction. By this I mean, and I will show you in detail, we can look at the diffraction events or we can look at imaging events. We can look at imaging events with a wide range of magnifications from as low as 50 times to as high as 15 million times. So that's an extraordinary range of magnification. Again, useful for characterizing materials. The microscope is generally set up to have a region that gives you the electrons. That's the electron gun, they call it. The electrons come down to your sample with a wide range of energies. It's not uncommon to have machines that vary between 300,000 volts of incident energy down to as low as 80,000 volts, or different types of microscopes will even go as low as 30,000 volts. So the difference in voltage gives you differences in penetration, but of course also differences in voltage change the way that the electrons interact and can change the relative amount of damage that you have. Below the electron gun, you see the condenser system. This is the portion of the microscope that allows you to control the size of the beam that you are using to impinge upon the sample. The objective region is your primary imaging lens. That's the one that gives us both diffraction and magnification information. And then in the projector series, there's 4 or 5 different lenses that allow you to magnify either the diffraction pattern or the image down onto some form of imaging media. This is an old cross-section here, one of the better ones from a machine that's almost 30 years old. And you can see even in this old, relatively simple machine, there's lots of lenses and a lot's going on. The microscope is, as a result of all of this, not a small entity. Here's an example of a 200,000 volt machine that's existent at the CFN at Brookhaven, a Joule 2100F. So again, you see at the top, the electron gun. You see the condenser system, which is the little shiny part there, passing down into a series of lenses. Off to the side, you see a thing that looks like a tube. That's where your sample comes in. That's the primary objective lens. And then a series of lenses for magnification and a little screen down there that looks down onto a phosphor so that you can see the electrons impinge upon the phosphor. And then there's a series of cameras and other items below there so that you can detect the electrons that are there. Okay. So what I want to do for a period of time is talk about how a TEM works, and then we'll go through and talk about how we use it after we understand how it works. So the TEM has kind of analogies to an optical microscope. In our case, instead of a source of light, we have a source of electrons. Again, a condenser system in this highly simplified version here, 2 lenses that allow you to change the way that the electrons come down upon the specimen, an objective system for the primary imaging, and a series of additional lenses that allow you to magnify. At the very end, you'll have some form of detector for looking at the diffraction pattern, the image, or perhaps for looking at various spectroscopic events. To further think about this in terms of the analogies with an optical microscope, these are some slides that I stole from the FEI Corporation. Nicely done, actually. So here's a standard optical microscope in the transmission mode, right? Your eye sits down on top of a projector lens, a magnifying lens. You have light from the bottom. It comes through to a single condenser lens that focuses that light onto your sample, your glass slide. The light passes through your sample up to the first objective lens, the primary magnification lens. So if you think about the use of the optical microscope, when you change from one click, 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 you're changing from, say, 5 times, 10 times, 20 times magnification. That's the primary imaging lens, the objective lens. And then thereafter, you'll have 1 or 2 additional lenses that magnify that further until it reaches the detector, which in this case is your eye. In the TEM, things are somewhat upside down, generally. Your light source is instead an electron source. It sits at the top of the microscope. The electrons pass through the condenser lens series to, again, allow them to focus down onto the sample. The objective lens is the primary imaging lens. And in this case, instead of switching our objective lens to get different magnifications, what we do is change the relative strength of these series of lenses below the objective in order to magnify the overall image that we see. And in this case, again, instead of having your eye as a detector, we use specific types of media that interact with electrons in order to provide an image or diffraction pattern. So that's a TEM. That's how it works. I think the thing to do next is to make sure there's no questions. I really do welcome questions. It's a little easier to answer questions than to simply talk at a screen for a while. But if not, we'll move on to kind of talking about the types of signals that we get using electron microscopy. Okay, so as I mentioned, because electrons are very strongly, the electrons strongly scatter with matter, we need to have a very thin sample. And the question, of course, is how thin? Well, you can look at something as thin as an atomic layer of graphene, or up to about a micron thick. Anything thicker than a micron tends to be so thick that the electrons undergo multiple scattering events and no longer pass through the other side and are detected. So this, of course, implies something. It implies that in order to do transmission electron microscopy, you need to either have a sample that is already very thin, or you need to find a way to make it very thin. I'll talk at the very end of the presentation about one way of doing that, but there's a variety of different approaches, including simple things like literally grinding it down with a very fine sandpaper, using electrochemical methods for things that are metallic, using impinging ions in order to thin the material. But in the end, you need a sample that's thin enough that the electrons can transmit all the way through. So if you have this case, you bring in then an incident high kV electron, something that varies again from, say, 30 kV at the lowest to as high as 300,000 volts. As an aside, there are several machines around the world that go to 1 million or more volts. Those are used specifically to try to look at very thick samples. But this incident high energy electron has many things that can happen as a result of interacting with the sample. The simplest one is that it can simply transmit through. If your sample is thin, there's a probability of electrons interacting, but they may instead just pass straight on through without seeing any of the atoms. We call this the direct or transmitted electron beam. Now, in addition to this, we can have electrons that scatter off of the atoms, either the nucleus or the electron cloud. And there's 2 modes that they can do it. They can scatter with no loss of energy. So these are elastically scattered electrons. The 200 kV that comes in interacts with the atom and leaves at 200 kV. We can also have inelastically scattered electrons. The incident electron comes in, has an interaction with either the nucleus or more commonly with the electron cloud, and then loses some energy and then scatters down through the sample. You'll recognize this as something that you've seen before when you talked about X-ray absorption spectroscopy, right, where you had X-rays coming in and interacting with the electron cloud. and leading to X-ray fluorescence events. Well, in this case, the incident electrons can do the same thing. They can interact with the electron cloud and lead to X-ray fluorescence. But of course, in so doing, they lose some energy and are inelastically scattered forward. If you have a case where the incident electron sees the nucleus, it can even go through a backscattering event. And of course, if you know the history of physics, right, that was the Rutherford discovery, right, was that if you streamed electrons at a material, every once in a while they would bounce back at you, and that was proof of the discrete nature of atoms. So we can take advantage of backscattered electrons. In addition, when the incident electron comes in and interacts with the electron cloud and causes that X-ray fluorescence event, it's knocking an electron out of the outer shells, and those electrons can then move off into space, and those are so-called secondary electrons. So if you've ever heard of or used an SEM, in the case of the scanning electron microscope, you're using either the secondary electrons or the backscattered electrons off of a thick sample in order to do your imaging. In the transmission electron microscope, we tend to focus on those that transmit through the sample, although some machines will have a secondary electron detector within them. Now, there are other events that can happen as a result of having that inelastic scattering event. As I mentioned, you can see characteristic X-ray fluorescence, emission. So the characteristic X-rays that come off of the sample can be detected. Also, by having the electrons come in and interact with the nucleus, you can see them slow down as a result of that interaction. This leads to so-called Bremsstrahlung or background braking radiation. This is basically a noise that interacts with our specimen and our detection of X-rays. And in addition, you can see Auger electrons, again, something you learned about in a prior class when we were talking about X-ray photoelectron spectroscopy. We do not tend to deal with Auger electrons in our systems, largely just because we don't tend to have good enough vacuum to see much out of those. It's also possible to see electron hole pairs be created if you have a semiconducting material. And if you have a direct bandgap semiconductor, you can even see light emission as a result of the electrons interacting with the sample. So if you look at this, this is a wide range of signals. If you put it in the context of your prior lectures, you might be interested in characteristic X-rays. If so, right, in that case, you would go to a beamline that has an X-ray fluorescence detector, and that's the sort of work that you would do, was to look at the X-ray fluorescence. If you wanted to do imaging, you might go to the hard X-ray nanoprobe beamline or the SRX beamline. In that case, right, you would be using things like a focusing optic to help you image. You might be interested in looking at visible light photons. So that may be another route. The important point of this is that within the TEM, as a result of the wide range of signals that you get, there's lots that you can do. And so I really want to just kind of finish off there and say that, that's the main thing to talk about. So the primary rest of the lecture is going to talk about how we image, how we get diffraction events, and how we look at inelastically scattered X-ray electrons and the characteristic X-rays that come off of the sample in order to characterize materials. So again, I haven't gone through a lot of slides because I'm trying to really get these key points at the beginning about how the microscope works and the types of signals that you can get. Again, if there's any questions, feel free to ask them in the Q&A. Okay, if not, I'll move on to diffraction. So just like you learned from Bob Sweet in one of your first lectures in the class, if you have a X-ray that comes in, right, it's a wave, of course, and a particle both, but if you think about the wave-like nature of it, you can see the waves will come in, they will interact with the planes of the atoms in the sample. You will see in the far field particular directions where you see constructive interference. The same thing happens in the TEM, but the geometry is specific. In this case, if you have our very thin sample and your planes are aligned in some direction, if they have an angle such that the incident beam is at the Bragg angle, you will see in the far field Bragg diffraction events. In this case, in the transmission mode, it's noteworthy that because of the fact that we have a 100,000 volt or more electron, our wavelengths are very small, and this means that the Bragg angles that we're dealing with are very small as well. So a way of thinking about this is that the sample acts as a grating, a diffraction grating. Our incident electrons come in, they transmit through to the direct beam due to the fact that they may not interact, but if they do scatter at specific small angles away from that direct beam, we will see specific points where Bragg diffraction has occurred. So it's worth then again noting that we will see not only a central spot, but a series of diffracted beams wherever the Bragg angle is met with respect to the incident beam. I'm not going to talk any more about diffraction because you had a whole lecture on it. I think the whole important point here is that in our case, we're dealing with thin samples where the transmitted beam passes through, and we see a series of diffracted beams depending upon the orientation of our sample with respect to the incident beam. That then determines which Bragg planes are selected and give constructive interference, okay? So with this, you then need to figure out, well, how do we look at diffraction? Well, it turns out that in the case of electrons, we can use a lens, place that lens after the sample. It's an electromagnetic lens. Electromagnetic lenses have the property of being convex lenses. It's not possible to create a single lens that's concave with an electromagnetic lens. They're all convex. And so what you see is you see something like this. If you bring in your parallel beam, you have your sample, you'll see the transmitted beams coming straight out, and you'll see some set of diffracted beams coming off at specific Bragg angles, right? So this is represented here with the incident beam being the two lines coming in, the direct beam, and a set of Bragg angles. For a convex lens that's placed after the sample, it will capture these scattering events, these diffraction events, and the nature of a convex lens is such that parallel rays that are brought into a convex lens will be focused at a specific point after the lens. That's called the back focal plane. And then if they propagate further down the microscope, there's a separate plane where they rejoin all of the other beams that came from the same part of the sample, and that's where you form an image. So a way of looking at this is that because of the action of the lens, the parallel rays are brought to focus at the same point in the back focal plane, and that means that the back focal plane is where the diffraction information is present. To say this differently, every time you bring a parallel beam of electrons into a thin sample, there will be some Bragg angles that are satisfied. Those parallel rays that come out as a result of Bragg scattering will get focused to a specific point in the back focal plane, and that's where we can see a collection of all the diffraction events. So we have the good fortune in the electron microscope of being able to place lenses further down the electron beam column and capture or make an image of that diffraction pattern. So what we do is we basically place a series of lenses, and we choose to make the back focal plane our new object plane. And then we take that object plane and we magnify it down onto some detection media. So we use the subsequent lenses to image the back focal plane, magnify it onto an electron detector, and in other words, that diffraction pattern becomes the image. So as a result, every time that you place a crystalline material inside of a TEM, you will necessarily see the diffraction events in the back focal plane of the objective lens. So that's great. It means that you can always look at a diffraction event. You can always get a diffraction pattern for any sample you put in the TEM. So just to clarify, if you're looking to do that within a beamline at NSLS2, you would need to go to a beamline that's set up for doing diffraction. It's not possible to then subsequently image, right, the same areas. So what do our diffraction patterns look like? This is a particularly pretty and relatively complex diffraction pattern. This is, as at the time, it happened to be on a piece of film. It's an old pattern. But you see a very bright central spot. That's the direct beam, the one that transmitted through without diffracting to first order. And then you see a series of spots in space, and each of those spots corresponds to diffraction from a particular plane within the sample. So you can see that there's both a distance away from the zero beam as well as an angle, right? And so the diffraction information here tells you about what the D spacings are, as well as their orientations with respect to each other. This particularly complex pattern is taken from a material that was grown called gallium nitride, and it was actually a bad growth. It was a growth where someone was trying to make a sequential layer of hexagonal gallium nitride with a wurtzite structure, and then cubic gallium nitride with the kind of sphalerite structure, and they failed. They did get both structures, but instead they were intertwined with each other, and this complex pattern is a result of that. But it's kind of interesting. You can see specific symmetries, right? You see streaks in particular directions. Those streaks have to do with so-called shape factor effects, indicating there are twins in the sample. But if you look at the information here and you analyze it, you can learn a tremendous amount about the sample. And really everything I just said, the fact that it's hexagonal gallium nitride, it actually has two twin variants of cubic gallium nitride. The extensive twinning is apparent from the thin streaks in multiple directions, and you can even know what type of directions based on the analysis of this pattern. So very neat. If you do not have a polycrystal or a textured material, your pattern will look different. So here, right, if we look at the top one, this is a randomly oriented polycrystal. And again, this should be familiar to you from the X-ray PDF lecture that Eric Doherty gave. Same idea. We're looking, instead of having a Lowy X-ray pattern where you see rings, we're seeing a bunch of randomly oriented crystals giving specific spots, right, to specific Bragg angles. And because of the true random nature of this, you see a intensity ring where the distance from the zero beam to a given ring is associated with the D spacing. You could again average this right around the ring, form a standard Bragg-Bertano type of geometry where you see peaks and measure that off. So in small grain samples with a random distribution, you'll see the same sort of thing that you would see from a larger material in an X-ray PDF experiment. And again, like Eric Doherty mentioned in his lecture, it's not always true that the distribution of orientations is truly random. Sometimes you will have preferred directions. In this case, you will see, like you see in the bottom pattern, where there's an arc of intensity along a preferred direction. In this case, happening as a result of taking a piece of steel and cold rolling it, deforming it so that it has a primary set of planes oriented in this particular direction. Right, so just exactly the same as you see with X-ray PDF type of work. Also, if you have an amorphous material, you will not see Bragg diffraction because there's no crystallographic planes. Instead, what you'll see is you'll see a scattering pattern. Amorphous materials do not have a random placement of atoms. They instead have specific common distances. And so if you look in the back focal plane of a, if you have an amorphous material and you look in the back focal plane of the convex lens of the microscope, you'll see this type of pattern. And if you go through and average around that radial distance, you'll see what's called a radial distribution function. And this can be recorded and measured. And it tells you about the probability of having atoms at a given distance from each other. So that's another type of pattern that you can see. Now, you haven't learned about this next one in any of the lectures to date because, well, frankly, because it's not really easy to do it with X-rays. As I mentioned, the condenser lens can be used to bring down the beam onto the sample in a variety of ways. In the first couple of diffraction patterns I've shown, it's been a parallel beam, right? A single valued incident wave vector that gives you specific angles of Bragg diffraction. Because of the fact that we have multiple lenses in advance of the sample, we can also take the beam and converge it into a cone of illumination and then place that cone of illumination onto the sample. The result of this is, instead of having a single valued wave vector, we actually have a cone of wave vectors, a converged beam. Now, this is it takes a little time to go through all the details, but a way of thinking about this is that instead of having a single incident valued K or incident valued wave vector, that gives you the single shell of the A-volt sphere that you learned about from Bob Sweet. Now we actually have a thickness to that A-volt sphere because you have multiple valued K sub i's coming into the sample. The result of this is that as you have a thickness, you begin to sample the three-dimensional diffraction space, the reciprocal space, and you see, well, first of all, beautiful patterns, but you also are able to capture the inherent symmetry of crystals. So this is a silicon 111 pattern, looking down the 111 zone axis, and if you look closely at the center there, you will see that there's a threefold symmetry, pardon me, a triangle, right, reflective of the fact that 111 has a 3-bar symmetry and not a 6-fold symmetry. Notably, if you look at the spots, the larger disks around the central beam there, you'll see that there's 6 of them, and that's because, right, Fresnel diffraction, a transmission diffraction, tells you that you have a loss of that bar symmetry, the inversion symmetry. So it's interesting that if you look at a 111 spot pattern, you will see a 6-fold symmetry, but if you use a convergent beam pattern, you're actually able to capture the correct symmetry, the 3-fold symmetry that's present in the sample. So convergent beam diffraction is used for looking at symmetries. You can actually work through the entire point and space group determination using convergent beam diffraction. You can do local strain measurements because it turns out that that little triangle, for example, if you change the lattice parameter, it'll dilate and give you information about strain. And also, just because of the ability to focus the probe to a very small size, including down to the angstrom scale, you can get diffraction from extremely small bodies of material. Again, something that's challenging to do with any other technique. I'll show you this again largely because it's pretty, not because it's extremely common, but you can actually combine image and diffraction information by choosing where you look. If you look between the back focal plane and the image plane, you actually impose the diffraction information upon the sample. And again, you can use this to understand things like misorientations across grain boundaries, defect characters, as well as crystalline symmetry. This is called a large angle convergent beam pattern. Not going to spend a lot of time on it. Okay, so let's talk now about imaging. Maybe I'll stop just to make sure if there's any questions about diffraction before we go further. No open questions. Okay. So let's talk now about imaging. One of the key strengths of the TEM is the fact that not only do you form a diffraction pattern in the back focal plane, you also form an image in the conjugate image plane, right? And so what we can do is we can choose a different strength to the next lens, the intermediate lens, and instead of looking further up the microscope and making the back focal plane our image for subsequent magnification, we can weaken the intermediate lens and look at the image plane and magnify that. And so then, as a result, we can take an image of our sample and the electron interactions within our sample. Because we have 1, 2, 3, 4 lenses in that set of magnifying lenses, we can vary the magnification from, as I say, 50,000 times to up to 1,000,000 times or more. At 1,000,000 or more times, this allows imaging at the angstrom level if the lenses are good enough, which people spend a lot of time making them good enough. So this really is a key thing, right? Importantly, because of the fact that you have your sample, your parallel rays, your diffraction events getting brought to the back focal plane and then propagating further down to the image plane, it means that every image you obtain in the TEM carries the memory of the diffraction events that caused it. In other words, every time that you have an image, it's possible to correlate the things you see in the image with diffraction events. This is an incredibly powerful thing. And in fact, it's the key point as to why the TEM is so very useful. What it means is it means that we can obtain diffraction information from specific small areas. We can look at our image and say, huh, I wonder what that thing is, and then go back and look at the diffraction information from just that region of the sample. Or we can look at our image and allow only certain diffraction events to contribute to our image. So that's an incredibly powerful thing. It means that the images we have not only magnify, but they carry diffraction information that we can exploit to further understand our crystal structure. So that's really the key to imaging and diffraction in the TEM. So you might ask, well, how do we go about doing that? Well, one thing that we can do is we can form what's called a diffraction contrast image. In the case of a diffraction contrast image, what we do is we selectively tilt our crystal so that we primarily have diffraction off of just one Bragg beam. This is called a two-beam condition. It's a two-beam condition because we always have the transmitted beam coming along the optic axis of the lens. But by selectively choosing how we tilt the crystal, we can choose to have one set of planes in a strong diffracting condition. The result of this is that if we would like to understand how that diffraction event manifests itself in the image, what we do is we place what's called an aperture in the back focal plane. And an aperture is nothing more than a strip of metal with a small hole drilled in it. And so you literally go and in the microscope, you twist a little knob and you place in a metal with a hole and you selectively move it around until it captures just the direct beam. And the result of that is that if you're doing this, you form what's called a bright field image. And the result is that you see a bright image everywhere except for where in the sample the diffraction events are occurring strongly. So if you had a sample that had a particular type of defect, where that type of defect strongly diffracted into a particular direction, you would be eliminating that set of rays from contributing to the image that forms thereafter. So looking at this here, this objective aperture in the back focal plane cuts off the contribution of all rays except for those going down through the optic axis. And that means that what you'll see is an image that has has bright intensity everywhere except for where the strong diffraction occurs. So if we go back, which I think I have a harder time doing in this navigator mode, so I'm going to crash out of this just real quick and go back, right? If we look at the imaging mode here, right, you see, again, the idea of parallel beams being brought to the back focal plane and then forming the image thereafter. In this case, I have a large objective aperture that's allowing all of the beams to come through and contribute to the image. But in the case of using this for bright field image, we take that aperture and we make it smaller so that all that contributes is the direct beam to form the bright field image. We can also, instead, move the aperture over to the diffracted beam and selectively use it to give us information about our sample. In this case, we're forming what's called a dark field image, and we get a black image except for the areas that are selectively diffracting to this beam. This is, again, a nice way of understanding the different features in your sample. There's a subvariant of this called weak beam dark field that you may see in the literature. It's a way of manipulating reciprocal space to give you a slightly higher resolution version of this. You tend to use, instead of the diffracted beam, you use the opposite beam 3 times removed. Don't want to talk about it other than to say that you may see that there. One of the things that we tend to do when forming diffraction contrast images in the dark field mode is it turns out that the way that these lenses work is they're not as good if you have beams off the optic axis. They have aberrations that are present. So generally when we form a dark field image, we'll tilt the incident beam at the Bragg angle so that we direct the diffracted beam along the optic axis. That's a minor point for this class, but just something to note. So what do we see? Here's an example of a typical bright field image. In this case, we're transmitting our beam through a sample that has a bulk silicon crystal. By bulk, I mean, a couple hundred nanometers, and then a thin silicon germanium layer on top of it. That silicon germanium layer is strained with respect to the silicon. And one of the ways that the strain is released is through the formation of a particular defect called a dislocation. Dislocations are important. They are the media the mechanism by which plastic deformation, bending of crystals occurs. So in this case, you're seeing these black lines on a bright background because these regions of the crystal that are dislocated or slipped with respect to each other are preferentially diffracting the beam along a particular direction. Okay, and so by placing an aperture around the direct beam, you're seeing the result of having strong diffraction around these individual dislocation features, and thus you can image them. Again, this is important in the fields of mechanical metallurgy because dislocations are the media by which plastic deformation occurs. And what you can do is, with careful work, you can tilt to a variety of different crystalline orientations, understand the ways that dislocations show up, because that's reflective of the crystallography of their slip planes and their directions of slip, and use this to characterize the types of defects that are present in a sample. So if you're a mechanical metallurgist, this is the sort of work you do and care about. It's also possible to use this type of imaging to understand stacking faults, which are where there are faults in the crystalline orientation from having crystal defects during growth. Grain boundaries, where different grains come together. Importantly, it's a way to understand where precipitates are. Precipitates are secondary materials embedded within a matrix. If you think about how an airplane flies, it flies because you have aluminum that's reinforced with a copper precipitate, aluminum copper precipitates. So you can image their location, their type, their character, other types of secondary phases. So diffraction contrast imaging is an extremely important way of using the electron microscope. So just to give you a bit better sense of that, a dislocation, right? It's a defect that allows crystalline slip. Here's a model of a dislocation. It turns out that what a dislocation is an extra half plane of atoms that are present. It has a core, right? That black line that you were seeing was reflective of that core. And when you do deformation in a crystal, what you're doing is you're basically taking and shearing a material, and it turns out it's easier to like flip those atoms over at that extra half plane and propagate that than it is to move or slice through the entire crystal. And so plastic deformation occurs by the motion of dislocations. But because it's an extra half plane that's jammed within the crystal structure, it strains the crystal structure locally and leads to changes in the local diffraction conditions. So this is why we see what we see is in the areas of perfect crystal, your diffraction conditions are different than they are local to that defect. And so we selectively tilt the sample to enhance the scatter from the defects. We can do this in systematic ways through knowledge of crystallography. And then again, by choosing either the transmitted beam for the bright field mode or the diffracted beam for the dark field mode, we'll see where those dislocations are. The result, again, is a contrast that's local to the defect. Okay? So let's take some more images of that, or pictures of that. Here's a case of gallium nitride. Gallium nitride is a crystal that is often grown on alumina. It's a very important material. Gallium nitride is the material that's used for green LEDs. It's the material that's used for the white LEDs that you now purchase to light your home. It's so important that its discovery in 1995 range led to a Nobel Prize for Shuji Nakamura and colleagues. So an important crystal. So these are some older images that I took back when people were really understanding these sorts of things, and I was working on it a lot. You can again see, here's a series of 3 types of images: a bright field image on the left, a dark field image on the right, and a so-called weak beam image on the far right. Bright field on the left, dark field in the middle, weak beam on the right. You can see several really interesting features. You see these black lines coming through the bright regions of the crystals on the left. Those are the dislocation defects. On the case on the far right, you see that everything's kind of a light gray with very bright white lines that are very narrow. That's the weak beam dark field image. Again, it shows you that gallium nitride grown on alumina can be highly defective. One of the interesting things about this material is, despite the high defect densities, it's still able to produce photons under an applied bias. The other thing that's kind of neat about this is, if you look at the bright field and dark field images on the left and in the middle, you'll notice that it looks like there's kind of some changes of these tall columnar features as you go from left to right to left to right. And so you see a kind of a darkish region, a whitish region, a darkish region, and a whitish region. That actually tells you that the gallium nitride is not growing as a perfect single crystal, but rather growing as extremely well-aligned, oriented columnar grains. And so when people grow gallium nitride, they talk about the growth of single crystal gallium nitride. It's actually a very, very, very highly textured, nearly perfectly textured set of grains in the crystal. So this, you can see from these types of images, there's lots that you can learn. If you even look down towards the bottom portion of the image, you see a straight line running across there. That's because during the course of this crystal growth, the folks went through and took a pause, right? And they actually put in a single layer of a different material there in an attempt to reduce the dislocation densities, which you do see a little bit. And this is kind of one of the things we were studying at the time. Okay. So that's diffraction contrast imaging. It's a neat type of image because, again, it gives you a direct relationship between the things that you see and the diffraction events that cause them. Really exploiting the power of the TEM and the convex lens that's present as your primary imaging lens. Okay, sorry about the phone call in the background. Okay, so next I want to talk about two modes by which we do atomic resolution imaging, and then we'll take a pause and a little bit of a break. So we have two ways that we do atomic resolution in the TEM. The first of them is called phase contrast, and I'm just going to give you a general idea on how this works. The idea behind phase contrast high resolution TEM is that we have our sample, it's very thin. The thinner the better in this case. And what we do is we use our condenser lenses to bring down the beam in a parallel fashion so that we're bringing in an incident electron wave that has a single valued incident wave vector, right, a given wavelength. This then comes into the sample. It sees the sample, and it can do a variety of things. The first of which is it can transmit through to the other side. It sees the sample, it actually undergo a phase shift as a result of having the media present. A way of thinking about this is that if you bring light into glass, it will have a phase shift. That's what causes refraction and refraction. But in particular, you see a transmitted beam come out the other side. If you orient your crystal so that you're imaging along a zone axis, what you will also see is you'll see many different diffracted waves come out from the specific angles that satisfy the Bragg condition. And so as a result, what happens is that your thin sample effectively acts as a phase grating. It takes and transmits a single valued wave into a series of transmitted and diffracted waves. And what we do is we let those propagate down and we image their interference, the way that the phases both constructively and destructively interfere to form our high resolution image. So what do we get on the other side? Well, this is a particularly pretty version. It's been massaged a teeny bit through some filtering, but you see here, again, the interface between gallium nitride and sapphire at the atomic scale. So on the left-hand side, you're seeing gallium nitride, and the individual white dots that you are seeing are reflective of areas where there is constructive interference in this type of imaging mode, and areas that are black or where there's destructive interference. The white dots are actually where the atoms are. In this case, where the gallium atoms are. There's a little bit of nitrogen present there too, but mostly the gallium because it's the heavy atoms. You see the sapphire on the right. Sapphire has a different crystal structure, and thus you see a different pattern. And you also see the interface between the two, and you see that it's pretty darn perfect, right? There's no amorphous material. You see some changes at the pattern between the sapphire and the gallium nitride. As these two crystals kind of interact, the gallium nitride begins to grow on a slightly roughened surface. But again, this type of image, a phase contrast, high resolution image, allows you to see where the atoms are in the sample. Just as another example here, you can see, in this case, you can combine the diffraction contrast imaging and high resolution imaging modes to learn even more. If you look here on the upper left, you've chosen a bright field image in one condition, in the upper right, a bright field condition in another area. You use this again to look at the types of defects that are present. Then you can combine this with high resolution imaging in the bottom to look at the individual. In this case, I believe this is a indium gallium arsenide quantum dot grown on gallium arsenide. Again, very lovely to combine the two to give you an overall feel for the sample as well as an atomic level description of the interfaces between the different materials. Another example here on the left, a low magnification image. It does happen to have atomic resolution, but you again see in this case stacking faults. And then if you look over on the right, this is a high resolution image that shows you what those stacking faults look like at the atomic scale. You see that you go from AB, 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 AB stacking to having BC, AB, AB. So that stacking fault from A, B, C, A, C, A, C, right, is indicative of a change in the crystal structure. So these are the sorts of things that one can do with high resolution imaging in the phase contrast mode. Now this mode is still used frequently, but over the recent years, it's become a little less popular as a new way of using the microscope has come into being. In particular, the so-called scanning TEM mode. So in the case of this mode, instead of taking our beam and placing it parallel to our sample and having the transmitted and diffracted beams interfere to form a phase, we take advantage of the fact that our microscopes have become so good that we can focus the beam down to a sub-angstrom point and scan it across our sample. And what we see is we see the interaction of the beam with the atoms that are present. And because our probe, our electron, our focused electron probe is so small, we actually will get a situation where as we scan, we will scan along and we'll see, oh, atom core. And when we hit the atom core, the beam will scatter. It'll scatter to a variety of angles. And then when we go over further, oops, all of a sudden, we're no longer where the atoms are and the beam transmits through. We go further, we see another atomic column, boom, scatter to high angle, and so forth. And because our probe is so small, we can actually just go through and scan back and forth and hit atoms, go in between atoms, hit atoms, go in between atoms, and we'll form an atomic resolution image this way. We collect the scatter generally at high angles by using a scintillator detector called an annular dark field detector. Basically what it does is it's a donut that captures just the high angle scatter. And it turns out that because of the nature of scatter of electrons with atoms, the high angle scatter turns out to be sensitive to atomic number in such a way that heavy atoms scatter more strongly than light atoms. And this then gives us a imaging mode that's Z sensitive, atomic number sensitive. The high angle annular dark field mode thus allows you to take a direct picture of where the atoms are, but also gives you insight into the types of atoms. In this case here, we have a strontium titanate, lead titanate material that's been grown through molecular beam epitaxy. And you see where the lead is, because that's further down the periodic table. Things are brighter. This is false colored, but again, it's just false colored so that the brighter stuff is yellower. And you again are able to very cleanly look at the interfaces. You're able to see that there's some interdiffusion at the interfaces between the strontium titanate and lead titanate. Again, a beautiful atomic resolution image, right? Here's another example here taken from a nickel oxide material, or is this nickel cobalt? This is lithium cobalt oxide. I'm sorry, I forget which this is. It's a lithium ion battery material. And importantly, you can see differences in the crystal structure at the near surface as a result of the delithiation, and actually the lithiation in this case. And you again are able to look at the surface structure quite cleanly. It's important to note that you have a very directly interpretable image. Wherever you see that blob of intensity is where the atoms are, and it makes it very easy to kind of go through and work out the atomic scale structure. Okay? So I'm going to take a moment now, and I'm looking at 10 o'clock. I think I'm going to go ahead and offer an opportunity for a pause. And I don't know if Sal is still here, but I think this is a good point to pause. And I'm going to maybe ask everyone to come back at around 10 08. And of course, you're on different time zones. Come back in 10 minutes or so, okay? So let's take a break here.
Thank you. So let's take a 10-minute break, and we'll be back at 10:08 or 8 minutes past the hour, depending on your time zone.
Yep.
And if you have any questions, please write them in the Q&A, and we will answer them after the break.
Great.
All right. Thank you.
Things are coming through clear, Sal?
Yeah, everything is coming across clear.
Good, thanks. Okay. I'll keep my screen up, I guess.
Yeah, you could keep your screen up, and we'll just continue from here.
Okay. It seems like it's always hard to find the right moment to break. Let me grab a drink of water, Sal. I'll be back in a second.
Sure, no problem.
What do you think, Sal?
All right, so there are no questions in the Q&A section right now, so I guess we could just continue.
Okay. Questions are welcome, please. Okay, so I paused because I thought it was a good time to take a break, but let's go ahead and kind of remind ourselves where we were. We were talking about a new methodology, or the kind of preferred, increasingly preferred methodology for doing atomic resolution imaging. We take advantage of the fact that we're able to make really good electron lenses these days, and we can use those lenses to focus our beam down to a very, very small point, again at the angstrom to sub-angstrom scale. We scan that beam back and forth. It transmits through the sample, and if it interacts with an atom, it scatters to high angle, and they collect that high angle scatter, and then we use that to form an image. So we just basically build up the image point by point, and either we see an atom from the high angle scatter, or we see the absence of an atom, and we don't get intensity there. So this is called the high angle annular dark field, or Z contrast scanning TEM mode. Again, it turns out that the scatter mechanisms give you more scatter from heavier elements, and so you see that quite directly in the image. In this case, again, lead on strontium titanate. You see where the lead is because it's heavier than strontium, shows up more brightly. Again, very nice methodology, directly interpretable. Wherever you have a bright spot, that's where an atom column is. And again, you can use this to locate the atoms, see the crystal structure. But in addition to having high angle annular bright field images, dark field images, there's different types of ways of looking at that scatter. You can also instead collect the direct beam. That's called a bright field STEM image. You can collect the low angle scatter. That turns out to have some slightly different information. And so if you go to a modern STEM image instrument, it'll have a number of detectors and the ability to change the collection angle. In the bright field mode, a so-called annular bright field mode, low angle and high angle. In other words, we take advantage of the small probe and the ability to collect different types of scatter to form different types of images. Again, the most common is the high angle mode. Again, the image over here where the individual atomic species are apparent by the strength of their scatter. Here's another nice image on the right using aluminum nitride and gallium nitride in a multiple quantum well. Again, gallium further down the periodic table scatters more strongly than aluminum. You see that directly in the image as the regions that are bright and highly illuminated versus the dark background where the aluminum nitride is. So this is a very common mode for doing resolution imaging. In contrast, instead of looking at high angle annular, you can also look at the so-called annular bright field mode. Here you're collecting the scatter mostly near the direct beam, but absent the direct beam itself. And in this mode, it turns out that you actually preferentially see light elements. You can actually go through and use this to look at light species. They show up as a black blob on a white background, again, giving you an ability to nicely compare the high angle and low angle annular bright field images to look for both bright and both high Z and low Z elements. It's kind of a neat combination, and this is something that's only been around and used over the past decade or so. One of the first examples here from yttrium hydride, and if you look, the little teeny dot that's barely illuminated there is actually hydrogen. I think it's pretty amazing to think that you can go through and image individual hydrogen atoms using this mode. There's a variety of different ways that you can do this. There's a so-called medium angle, again, gives you slightly enhanced contrast, but all of these things are something that you can use in a modern microscope to allow you to image the individual atoms in their place. Another really neat development over the past couple of years is that people have learned how to make such good electron lenses that you can operate at very low voltages. At high voltages, it's easier to focus, but at low voltages, you have more effects from aberration. But in a modern instrument, you can even go down to as low as 30 kilovolts. And here's an example from our instrument here at Penn, where you're looking at a single layer of molybdenum diselenide, and you see the bright spots on the right from the molybdenum, the slightly dimmer spots in between from the sulfide, and you're really able to nicely and cleanly image these two in the annular bright field and high angle annular dark field modes. Okay, so that was the section on imaging, right? We have diffraction contrast, which allows us to understand how the diffraction events impose their information upon an image. And we have both the high resolution phase contrast and the high angle annular and other types of STEM imaging modes that allow you to see things at the atomic scale. Now, the other thing that's true is, in addition to having images formed, if you have our incident electrons come into our sample, they can scatter inelastically, and we can use that information to characterize our sample further. So returning to this view graph I showed at the beginning, our incident high energy electron can come in and undergo inelastically scattered events as a result of interacting with the atoms that are present in the sample. And we can utilize that information to learn new things. So as a reminder of some lectures you had earlier in the semester, if you have an atom, right, it has its core and it has a series of electron shells around it. Those electron shells have electrons distributed according to the laws of quantum mechanics. Just like with X-ray fluorescence, you can use incoming electrons to knock electrons out of bound states around the atom. Those incident electrons can come in, cause one of those bound states to be excited off into the conduction band or even as far off into the valence band. In our case, we're mostly looking at the conduction band. And in this case, you have then a situation where your atom is in an excited state, and it will preferentially take an atom from a higher energy state and bring it down to a lower energy state. And in so doing, it gives off a characteristic X-ray that has an energy associated with that difference between the states, right? So we again have incident electron coming in to ionize the atom, right? The electrons from the outer shell fills that hole in the inner shell. It results in the emission of an X-ray that is characteristic of the atom. Again, the energy levels are specific to the type of atom that's present, and thus the difference between the energy levels is as well. And this means that the X-rays that come off carry information about the atoms that the incident electron interacted with. Importantly, that incident electron may have come in with 100,000 volts, but after undergoing this collision, it loses an energy, and it loses a very specific energy, the amount of energy required to strip that electron from the core and place it into the conduction band. So we can, just like in the case of the beam lines at NSLS2, we can take advantage of this information and learn things about the chemistry of our sample. The easiest thing to do is to take and stick a detector near our sample and collect the characteristic X-rays, the fluorescent X-rays. In electron microscopy, we tend to call this energy dispersive X-ray spectroscopy, energy dispersive X-ray spectroscopy, but it's exactly the same as X-ray fluorescence spectroscopy. And again, just like X-ray fluorescence spectroscopy, what you see is you see specific peaks on a background of intensity Those peaks have specific values. Those values are characteristic of the atoms that are present in the sample, and you see quite directly which types of atoms you have. All you do is you look at the spectrum, and you see, for example, that you have a 9.8 keV peak, and that's associated by just simply going to a table and looking it up with uranium, second peak to the right at around 11 keV. And again, that's coincident with the K beta X-ray fluorescence emission. So just like with X-ray fluorescence spectroscopy at beamlines, we stick a detector in, we see these sorts of events, and we're happy to be able to characterize the chemistry of the sample. Right? I'll show some examples of this. If you think about this in the case of beamlines, what we're doing is we're generally bringing in a beam, and we may focus it, right? We learned about focusing to do fluorescence mapping. That's done at SRX, XFM, and the HXN beam lines at NSLS2. We can do the same thing with an electron microscope. So here we're looking at a case where we go through and we look at a crystal. In this case, this crystal is about, 30 nanometers in size. And what we do is we basically scan back and forth, and we collect the X-rays, and we map their location. In this case, it's an example of looking at palladium copper, and looking in particular how, as we go through and palladium, copper, and cobalt, in this case on the right, we see that if we expose the sample to a particular environment, there's a preference for the copper to be on the outside and the cobalt to retreat. But again, all of this can be done at the nanometer scale quite readily. But importantly, we can also do this at the atomic scale. Here's an example again from strontium titanate. In this case, we're looking at a high-angle annular dark field image on the left. You see the bright strontium atoms, the lighter titanium atoms. And if you take a subsection of this and scan for a while, you can actually detect the atomic columns quite directly by looking at the incident beam's interaction with the sample and the characteristic X-rays that come off. And you can map where the strontium atoms are, where the titanium's atom are, where the oxygen is, and via an overlay see that you can actually detect at the atomic scale. This is actually done at 30 keV in our instrument here. So even at low voltages, this is something that's possible. Another example here where you're showing the high angle annular dark field image, the bright field image. Again, you see in the high angle annular dark field, it's brighter where there's gallium, dimmer where there's aluminum arsenide. Complementary in the bright field image, it's brighter where there's aluminum arsenide versus the gallium arsenide. But you can also detect the X-rays that are coming off and see aluminum, gallium, arsenide all present. And again, do a nice overlay of that at the atomic scale. Helps to filter it a little bit to get rid of the noise. But again, a nice overlay of the high angle annular dark field image and the intensities coming from the aluminum, gallium, and arsenic, showing that you can really do atomic resolution, chemical characterization using the fluorescent X-rays, okay, using energy dispersive X-ray spectroscopy. So that's neat. Again, this is relatively new. The ability to have highly focused beams, good detectors, good stable microscopes has brought atomic resolution EDS into the kind of commonplace over the past 5 years or more. So that's just like X-ray fluorescence. In the equivalent mode, we can do the same thing as X-ray absorption spectroscopy. In this case, we're going to do what's called electron energy loss spectroscopy. As I said, if we have our incident electron come in and knock one of these electrons off of the shell, right, creating the characteristic X-rays as a result of that transmission, the incident electron loses an energy, and that energy loss is transmitted down through the column. What's interesting is the geometry of our setup is such that we have capture of the high angle scatter to form our image, but the incident electrons that undergo these inelastic scattering events are generally very forward scattered. So they're not collected by the annular dark field detector. And what we do is we place a spectrometer underneath, in our case, a magnetic spectrometer, that bends the electrons differently based on their energy loss. Effectively, what it does is it acts like a prism in the same way that white light comes into the prism and you get a ray of colors out the other side. In this case, we have our electrons come into our magnetic prism, and we color the electrons by their energy loss. And we see this on a detector as an electron energy loss spectrum. So here we are from this same sample. We see, in this case, it was neodymium gallium oxide grown on lanthanum strontium manganate. So this was chosen particularly because it's got a nice set of edges for the example. But you see the oxygen K edge, the manganese L23 edge, the lanthanum M45 edge, the neodymium M45 edge. The same things that you see in X-ray absorption spectroscopy are present in electron energy loss spectroscopy. Importantly, this is happening again with a 1 angstrom beam being scanned across the sample to form our 2D image. And so if we look, we can actually map out, again, point by point, and compare the high-angle annular dark field image with the individual scattering signals from lanthanum, manganese, neodymium, and oxygen, again giving us atomic resolution for our images in the high-angle annular dark field and electron energy loss spectrum. So again, able to take the electron microscope, see the atoms, but also color them according to their energy loss and do chemistry mapping at the atomic scale. Now you'll note, right, that we said that this was a edge, right? We look, right, for example, here, we see sharp edge onsets, right? In the same way we see for X-ray absorption, we're effectively doing electron absorption or electron inelastic scattering. We see the onset edges, right? We notice that they have a sharp onset. They're not a peak, they're an on followed by information thereafter. We learned from Bruce Revell that information is of 2 types, right? There's a near edge, which we call the Zanes in that case, and then there's also the extended loss fine structure. We see the same things here in electron energy loss. The reason for the near edge structure is for the same reason that we had in Zanes. It's that as we bring the incident electron in, we knock that one off of the shell, it goes into the conduction band, and it fills the available states in the conduction band. And so what we see in the near edge is the same thing, right? We see that we have information that tells us about the occupancy of the conduction band edge, right? And so we're able to map out the density of states. So this is just like Zanes. So we can learn the same things about oxidation state. We can learn about how oxidation and reduction of a material change the conduction band. But again, in the case of the EM, we can do this at the atomic scale. The next slide here shows that very cleanly. This is a beautiful paper that was taken off of the Hitachi instrument at the CFN at Brookhaven a number of years ago. Here, someone grew atomic scale strontium titanate, and they would put in a single layer of a transition, of the lanthanide material. Here, lanthanum oxide. This paper shows it for another of other lanthanides. This was done with molecular beam epitaxy. And what you can see is that if you can form the scanning TEM image, you see the bright region where the lanthanum oxide is or where the samarium oxide is, right? That's where the heavier element is, so it shows up bright in high-angle annular dark field. But also you can look at the L edges of titanium and the oxygen K edge, and you actually see slight differences in the reduction, oxidation state of the titanium and the oxygen local to that atomic layer. It turns out that they, again, have a slight dip in the titania for the lanthanum and the samarium versus the background in titanium. So importantly, this is Zanes, but it's like we call it, ELNES, electron energy loss near edge structure, but it's done at the atomic scale, which is again very powerful in appropriate samples. Another nice example of mapping shown here for an indium gallium nitride layer. And again, you can map out point by point at the atomic scale where the gallium is by looking at the L edge, where the indium is by looking at the M edge, and where the nitrogen is, i.e. everywhere, again at the atomic scale. So beautiful examples of near edge mapping using electron energy loss spectroscopy. Now, it turns out that there's even more that happens in eels. If you happen to have a good microscope with a good energy resolution and a good spectrometer, you can also look at the so-called plasmon. I'm going to go back in Navigator here, and I think I'll just go ahead and do what I was going to do. Plasmons represent the oscillation of the free electron gas. We're often looking at plasmons these days because they're ways of altering things like local surface chemistry. They modify the way that light interacts with materials, and there's a lot of interest in understanding plasmonic effects. So here what you do is you actually look at the region near the zero loss beam, the beam that transmitted through without an energy loss. And at very small energies above that, that's where plasmons or local electric field effects are apparent. And again, you can go through and map using eels, choose ranges of the eel spectrum, and kind of display where there's local plasmonic interactions. So this is a beautiful example from a paper done again at the CFN, where someone brought in some gold features. These are relatively large prisms and hexagonal features of gold. And what you see is that the presence of sharp edges leads to, and shapes overall, leads to changes in the plasmonic modes that you can actually map out using electron energy loss spectroscopy. There's also, if you have an extremely good microscope, there's about 1, 2, 3, 4, 5 present in the world right now that have extremely good energy loss capabilities. They're designed to do this type of experiment. There's one at Rutgers. It was the first, and I say nearby because that's just up the road from Penn and down the road from Brookhaven. It's a unique instrument that actually has a 0.01 EV, and that actually allows you to look at things like phonons. Not an easy experiment, but it can be done because they have resolutions that allow you to extract as low as 40 millielectron volts. Okay? So I would like to recognize a question, so thank you so much. There was a question, is it possible to look at frozen solution samples to probe large individual molecules? Yes, it is. So I will be honest and say that I'm preferentially giving a lecture on using the electron microscope for materials applications, and that's because I'm a material scientist and not a biologist. It's possible to give another 2-hour lecture on the use of electron microscopes for doing biology. I'm not capable of that lecture, just to be frank. I took biology in 10th grade, last time. So, but there's a whole field of electron microscopy that uses the electron microscope to characterize frozen samples and to understand their structure and chemistry. In fact, that methodology was what was awarded the Nobel Prize in Chemistry in 2017, as it improved to the point of being able to do it at the angstrom or atomic scale. So I'm going to acknowledge the question, Rafael, and say that, if you would like, please reach out to me and I can point to a number of good lectures that you can find on the web that are specific to cryogenic samples for biological microscopy. And I just am not going to be able to cover it in detail here. So hopefully that helps, and give me a thumbs up if that's good enough, okay? We also do cryo in the TEM inorganic world for looking at soft matter, things like polymers and the like. And many of these same things can be done at reasonable levels of resolution, okay? The other thing to note is that STEM and eels are the same events, right? If you have our incident electron beam come in and produce that X-ray that you can detect, it loses the energy. They're complementary. This is a nice example showing that. Here's a case of eels, and here's a case of EDS. One of the nice advantages to eels is that if your sample is good and thin, most of the electrons that come into your sample and undergo these inelastic scattering events that create the X-rays, they're actually transmitted forward and collected by the eel spectrometer. So you tend to get better signal to noise in eels if your edges are well aligned with the detection. And so that's actually quite nice. Here's an example showing that you could see the same things in eels and EDS in a complementary fashion. And because of the way that the machine works, as you scan the beam back and forth, you can take the high angle annular dark field image, the annular bright field image, you can take the EELS information, you can take the EDS information, all at the same time, right? And use all that information to give you characterization of your sample. Here's a beautiful example here, again at 30 kV with our instrument, looking at a cross-section of a memory element, looking here at the annular dark field image, the oxygen K-edge, the nickel K-edge, the silicon K-edge in EELS, and here looking at it in EDS, again complementary. These complementary modes help you learn nice things by combining the information and confirming them. Here again showing a beautiful example from a former student of mine, Bob Colby, looking at lanthanum cobalt oxide and strontium titanate. Again, you see that you can use the information from EDS and EELS to help you understand the relative diffusivity of interfaces and combine that with contrast coming from the high angle annular dark field image mode. Okay, so chemical characterization is very possible in the electron microscope. It gives you a very nice way of kind of understanding the chemistry, not only where the atoms are, but just in the same way as XANES, it allows you to understand through near edge spectra where the different types of oxidation events are happening. So beautiful capabilities at the atomic to nanometer scale. Another final mode that you can use is you can use what's called energy filtered imaging. In the case of energy filtered imaging, what you do is instead of going point by point, you actually take and you use the spectrometer with a series of lenses after that to capture the beam and filter out just those electrons that have lost energy at particular modes. This has become less popular. It was a very popular way of doing things in the 90s through early 2000s. But as the STEM EELS mode became better and better, as we make better and better lenses, this has become a less common way forward. I just thought I would point it out as something that exists. Okay. Okay, so I'm going to maybe pause a minute and say, here's what we've learned so far. We have learned that we have a microscope that has lenses that allows us to focus and control the electrons that come into our sample. We can use that as a broad beam to allow us to image, to take diffraction patterns. We can focus that beam, again, to image in high angle annular dark field and atomic resolution. We can use that focused beam to get diffraction information from very small regions. We can use that focus beam to excite characteristic X-rays, measure them, and determine their composition. We can look at the electron energy loss events to determine spectroscopically what atoms cause those events, to learn about their near edge features for oxidation and reduction. So diffraction, imaging, chemistry with ranges of magnification so that we can do, atomic scale, nanometer scale, submicron scale, all through the same sample. So the microscope's very powerful, okay? I want to talk a little bit at the end about some other kind of neat ways of using the instrument that take advantage of this. A very fun one is the idea of doing electron tomography, right? So we learned about tomography in the last lecture, at least in our class by Xiaojing, where he was talking about doing tomography by taking the sample, right, and tilting it in multiple modes. We're able to do this same sort of work in the TEM, right? We basically bring in our incident beam. We generally use the high angle annular dark field mode for doing this because it's incoherent, which is a requirement for tomography. But basically we take our sample and we tilt it to a variety of different angles, and then we reconstruct the three-dimensional tomogram by bringing those information together using the exact same methods that were described earlier. The back projection images, the CERT, all of that was described by Xiaojing. So it's nice, and you can go through and do this in very nice ways. The other thing, just like we were talking about with other aspects of the class so far, is we can do dynamic imaging. In our case, because we have this very small region where the sample must sit in the objective lens, we actually bring in holders that capture all of these different dynamic events and possibilities within the microscope. We can do things like poke at samples for nanoindentation or nanomanipulation. We can magnetize samples to look at magnetic effects. We can bring in liquid flow in order to do electrochemistry. We can have machines that allow us to tilt the samples very regularly for tomography. And we can bias the samples electrically to look at things like how p-n junctions behave or light emission occurs. We can bring in gases to allow us to look at oxidation and reduction. We can heat samples. We can cool samples. All of these things that are possible inside of the microscope. And so dynamic experiments are a very popular thing in the modern world now that the microscopes are so effective. This is just showing a range of these that happen to be something that I've built over the years through a company I own, but there's a variety of companies that do this sort of work. Here's an example of how we might use this information. Right, here's chemical sensitive tomography, where what we've done is we've gone through and built up an image by basically capturing the sample at a variety of angles, capturing the EDS information, and using all of this to reconstruct over 3D where the cobalt is in the center, where the iron is more on the outside, how there's more oxygen outside with the iron, again, doing three-dimensional chemical sensitive tomography. But importantly, by having the ability to do this as a function of temperature, in this case, we're actually using eels, and we're looking at the time in these different slices that the iron cobalt particle has been exposed to oxygen. And in the case of this, we're looking at the mass contrast in top, the high angle annular dark field image. We're using eels to look at the iron and the cobalt, but also in the bottom, we're actually selectively looking at the ratio of the iron 2,3 versus iron in the non-reduced state, in the metallic state. And again, you see a preference for the outer shell having the F23 plus versus the inner part that's in the general metallic state, the FeO state. So here, a very complex experiment where we went through and took samples. We did tomography. We captured the eels information point by point at each tomographic step, reconstructed these in 3D, and then tracked this as a function of time in order to understand how these things occurred. And you'll note that the scale bar there at the bottom actually turns out to be 10 nanometers. So this is a relatively large particle for us, something like 30, 40 nanometers. But again, right at the point of what's very challenging for an X-ray. We can do lots of different types of experiments that are dynamic. We can do things like look at how electron beams interact with our sample. In this case, we were sculpting graphene nanoribbons using oxygen to help do that, see the atomic scale changes, and in particular, looking at how we can go through and correlate these features that we see in the image with changes in the electronic properties. It's possible to do liquid cell microscopy. Here's understanding how nanoparticles are guided by DNA through self-assembly. The idea here is that we bring in a sample holder that allows us to confine the liquid in a very thin region, thin enough that the electron beam can transmit. And we basically take time-lapsed movies of how the self-assembly process occurs in real time. We use these for doing studies of nanoparticle nucleation and growth. We use these for doing self-assembly studies, for looking at electrochemistry, looking at photoelectrochemistry, all within the sample. So again, I could spend a long amount of time talking about the variety of dynamic experiments that are possible, but I think maybe the best thing to recognize is that the same sorts of experiments that one might want to do using beamlines, you can do in the electron microscope in very nice ways. So I think as I'm looking where we are, I'm going to go ahead and maybe finish off by one little small section that's important. It didn't fit in anywhere else, but I think I want you to know a little bit about this, and that's the idea of how do we make a sample. I've emphasized that throughout, we need to have very thin samples. That's a special challenge, because not all samples want to be thinned, to the 10 nanometer to 100 nanometer range. Prior to kind of the 1995 through 2000 era, mostly the way that we made samples was with things like electrochemical etching, basically etching down to the point where we had a thick region that was etched all the way, and we would look around the thin hole using incident ion beams to thin regions of materials. But these days, we generally use what's called a focused ion beam microscope in order to do this. And the advantage of this is we can really use this to make both site-specific samples and, importantly, samples from more or less any material that you might want to make a sample from. It's another big, expensive, complex tool. You can spend $1.5 million or more for one of these. But again, we have 2 of them at the CFN of Brookhaven that you can use as you need to make samples. It's part of the same user facility process. So I thought I would show you this. It has, in this case, a electron beam for doing imaging, an SEM column. That's the one that's up and down on the kind of 57-degree angle off. That's the focused ion beam column. And what this allows you to do is it allows you to use, say, the SEM to take a picture of your sample. And you might think to yourself, I would like to image those dots. In this case, what it was a sample of lithium niobate that someone banged a laser locally, right, in order to create these surface features. And they were interested in seeing what happened at these surface features. So what we're able to do is use the focused ion beam to come out and stream ions into the sample. Ions are heavy, so they ablate the material. And we locally remove sections of the material, leaving behind a thin region. That thin region can be picked up with a little mini robot. It's just basically a little STM tip type thing. We pick that up with a little gripper, and then we cut the sample out, and then pick it up and move it over onto a support grid. And there it is there, right? This is an SEM image of that sample that has been specifically chosen in the region. And we can now go and take this thin sample, thin it even further, and bring it into the TEM for doing imaging, right? So the important point to take away from this is that although it's not simple to do TEM work, nearly any sample that you're interested in looking at, you can make a TEM sample that's thin enough for doing all the different things that I talked about. High resolution imaging. We're doing diffraction contrast imaging like what's shown here. We're doing EDS, we're doing EELS. And in this particular study, we did all of these, looking at the surface features that happened, understanding how morphization occurred, how distribution of elements changed through the sample. Okay, so that's what I wanted to talk about in terms of the TEM. I think I want to just finish up by letting you know the same sorts of things that you're going to learn about use of the instruments and capabilities at NSLS2. Just like NSLS2, there's a facility at Brookhaven called the Center for Functional Nanomaterials. It's on the same campus. It's literally next door. If you look carefully in this image where it says there's the little nameplate for the Center for Functional Nanomaterials and the building itself, the thing in the background is actually NSLS2, where the light is coming through at the dawn. It is a so-called nanoscience research center. It houses a wide variety of complex instruments for performing nanoscience work. In our facility, and I use R because I worked there some years, I don't work there anymore, but in the CFN, you have a number of different capabilities. You have material synthesis capabilities, specifically things like DNA-guided self-assembly. We have capabilities there for ultra-fast spectroscopy, full nanofabrication facility, including electron beam lithography. There's a facility for so-called proximal probes, like scanning tunneling microscopy, low-energy electron microscopy. There's a big computer cluster and people to help you with theory and computation. And interestingly, the CFN partners with NSLS2 on three end stations for X-ray scattering, for low-energy electron microscopy, and for ambient pressure X-ray spectroscopy. But in particular, I want to take a moment and talk about the electron microscopy capabilities, because that represents one of the major facilities within the CFN. And is, of course, important because this is what I've been talking about all day. So the CFN has 5 total electron microscopes. That represents about $20 million worth of equipment. They are, as shown on the left, a Joule 2100F analytical electron microscope. It's a very versatile instrument. It does TEM, it does STEM, it has EELS, it has EDS, it has a wide variety of dynamic microscopy capabilities. So that's actually one of our most commonly used instruments. In addition, there's the Hitachi. That's a probe-corrected STEM. That means that it has special electron optics in the condenser system that allow you to focus the beam down to that sub-angstrom probe. This machine will hit 0.78 angstroms at 200 kilovolts. It has EELS and EDS, and many of the beautiful atomic resolution images I showed in this talk were taken using this instrument. So that's a great capability. It's run by staff science. So importantly, each of these instruments have staff scientists associated with them that help you run the instruments. In other words, if you've never used a TEM before, but you really need to use a TEM, you can write a proposal to come and use one of these instruments, and someone will help guide you through the work. In the case of the Hitachi, you're specifically looking at how you might want to do atomic resolution imaging. There's two staff scientists who will help you do all of the work. There's a third instrument there in the middle. This is the Titan 8300 environmental TEM, very unique instrument. It has aberration correction below the sample, so it has ultra high resolution in the phase contrast mode, where your beam is broad, right, and you have the transmitted and diffractive waves coming together to form the phase contrast. This allows you to do high frame rate imaging, up to 1600 frames per second. Also, it allows you to do low dose imaging because of a very forefront detector on it. But most interestingly, if you look at that little box off to the side of the microscope, that allows you to stick gases directly around your sample. And so in this instrument, it's able to do hydrogen provision, oxygen provision. We're able to put in carbon-containing gases like CO2, methane, ethane, and the like. And that allows you to understand how materials interact with gaseous environments for catalysis, for oxidation, and the like. Very unique instrument. Dmitry Zakharov runs that instrument. And again, you don't have to learn how to use all that complicated stuff. You just need to tell people, this is what I want to do, and then the experiments are run for you. We also have a simple instrument for doing soft and biological materials. It operates at low voltage, so it's good for polymers and other soft matter. And then recently we installed a new instrument for so-called operando research. This instrument has a very bright source, EELS, EDS, 4 integrated EDS detectors for high sensitivity EDS. It has a high frame rate camera. It has a variety of, again, dynamic environments, including heating, liquid electrochemistry, atmospheric pressure catalysis. So a very versatile instrument for doing operando research, something that was installed just a number of years ago. The final thing I want to show you is that one of the things that has been developed at Brookhaven between the CFN and NSLS2 is a rather unique approach where we use these liquid cell and gas cell instruments for correlating information between beam lines and electron microscopes. So the idea here, this is not a simple experiment. This is something that requires a lot of planning and preparation. But if you would like, you can do things like use a focused X-ray probe at the XFM beam line or the SRX beam line to capture information such as the X-ray absorption spectra, the X-ray fine structure information from a sample. You can do X-ray diffraction, X-ray PDF. You can do, we've done IR spectroscopy, which is you're going to learn from Lisa Miller in the next lecture. All of that can be done at various beam lines across NSLS2. And then you can take that same sample and bring it over to that operando instrument I just showed you and do all the things that TEM can do. So you're able to do nanometer to atomic scale resolution and correlate the information you obtain from all of these different techniques. And so I think this is really an amazing capability that's really unique to Brookhaven. It maybe wasn't as unique as it was 2 years ago because people have been stealing the idea abroad, but in America, really, this is the place that you could do this sort of work. So if for some reason you have an electrochemistry experiment that you think could benefit from all of these techniques, you can write and do joint proposals to the CFN and NSLS2 to take advantage of these capabilities. Okay, so that's where that I think is really kind of a neat capability. And so I'm ending at 10:51, kind of as I had hoped, in order to allow opportunities for questions. I see one in the chat, so I will give you maybe start to answer some questions. So from Anicia, she said, in electron energy loss spectroscopy, what do the K L2, L3, and M2, L3 refer to? Okay, so thank you for that question. You will recall, just one moment. I'm going to have to take a minute to crash out of this. Forgive me. I'm going to open up a different set of slides just because I think it'll help answer that question. So you're looking at my rather busy calendar in the meantime. I of course teach a full semester on this technique, so I have a really good way to answer that question if you just give me one moment. Lectures and elastic scattering and okay. So Anicia, let me go maybe one more back here. This is a slightly more complicated version of that diagram, right? But we talked about the fact that
Eric, you're not on the screen share?
yeah, I am. Oh, okay. Oh, so I have to do that. Okay, so I have to reshare the screen. Thank you so much, Salvador. When I opened up a new presentation. So back to here. Great. And how's that?
There we go.
Thank you so much. Okay, so Anicia, when you bring the electron beam in, you're basically taking this high energy electron, and it has some probability of interacting with electrons within individual shells. Okay, so if you have an electron that comes in and interacts with an electron that's in the deepest state, the K state, right? You can have a transition subsequently from an L2 state down to the K state. Okay, that's one way that that excited atom can be satisfied, right? And so you see that shown here as an L2, that little black dot representing the electron there, right? Coming down to the K state. And it gives off a characteristic X-ray that's equal to EK, the energy of that bound state, minus the specific EL. That turns out to be what's called a K alpha 1 X-ray. Okay, so that's the name of that transition, right? And the X-ray that comes off. Okay, in a similar fashion, right? It's also a delineation of the inelastic scattering event and the energy loss that you see. So there's a whole set of spectroscopic notation associated with this. And yeah, this is an ugly looking diagram, but I just showed you the K alpha 1, right? That came from an electron out at the L shell, right? And down into the K shell. And so in the spectroscopic notation, that's called a K alpha 1 X-ray detected in EDS. But also in the inelastic scattering mode, that's what's called an L3 edge in eels, or it's also called an L3 edge in Zanes. Okay, so there's just different notations associated with the type of event that you have. So in the inelastic K edge, right, that's because you've got a K edge leaving from the core and coming all the way out into the conduction band. But if you have the L3 edge, it's leaving from L3 and going all the way out into the conduction band. So that's the difference between the different states, okay? And so, Anicia, if you could give me a thumbs up to let me know that that answered the question, or repeat the question, that would be great, okay? Anthony Rutherford asked, how easy is it to flip between the different techniques? Do you just switch a dial? The answer is yes and no. To go from diffraction to image, there's a button. You hit a button called diffraction, and all that does is change the intermediate lenses to go to the diffraction pattern, and when you hit the button for magnification, it goes back to the image mode, just like that. So it's incredibly powerful, the fact that you can just do this bing, 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 all right? High resolution TEM If you're operating in the diffraction and bright field mode, the phase contrast mode has the lenses all set up the same way, nothing to it. The stem mode, usually it takes a couple minutes to go from the phase contrast mode to the stem mode because you have to kind of re-optimize the condenser system. Back when I was younger, it took a long time, but the modern microscopes are so stable that you generally just load a pre-existing alignment and it's pretty close, and you tune one or two little things. Takes, for a good person like myself, a minute or two, and off you go, you're doing stem. Now, that's for standard modes. If you're doing the highest resolution in stem, you generally use a different microscope that's got a probe corrector. As I was just showing you at the CFN, there's the 2100F, the Talos. Those are not probe corrected. So their resolution's around 2 angstrom-ish, 1.8, 1.6, depending on the instrument and how good you are. But if you want to go to sub-angstrom, you need an aberration corrector. And generally, those aberration-corrected instruments just operate in the one mode, right? The high-angle annular dark field stem detector, stem instrument, that's all it does. But it also, of course, does the EDS and the EELs on top of it. So in answer to your question, Anthony, one of the reasons to go to and use the 2100 or the Talos is because they're so versatile. You can do diffraction, diffraction contrast, phase contrast, stem, EDS, and EELs, and that's great, you know. But what you might find is at the end of your session, you think to yourself, shoot, I wish I had a bit better resolution in the high-angle annular dark field. And so what you do is you take your sample out and you walk over and you go to the other microscope where you have to spend more time to get that extra little bit of capability, but you can do it readily. So again, hopefully that answers the question. You know, I'll give you the same comment I gave to Anicia if you want to let me know by scrolling down and give me a thumbs up. I actually have a hard time with these questions. I have a hard time seeing my mouse on the other screen that has the questions.
There's a question in the chat.
Yeah,
Regular chat.
There we go, great.
Soil sample, do you see it, or do you want me to read it?
Yeah, I see it now. A soil sample in polished resin can be suitable for tomography analysis, for mineral particles, for example. Yeah. So Renee, so great question. One of the things that's a constraint, so I mean, TM is wonderful, right? It does everything, like I just told you, as long as the sample's thin. And so you're saying if you take a soil sample and you have it in a resin, can you make a sample that's thin enough for tomography and do tomography with it? The answer is yes, but depending on the size of the moiety, the size of the thing that you're looking at, you may have to look at a subset of it, right? So if you had a particle that was, you know, a 10 micron particle embedded in resin, what you would need to do is go to the focused ion beam instrument and thin a section of that down, right? So that you could then put it in the TEM, have it thin enough to do all the work you wanted to do. So my answer to you would be, if your sample's big and your goal is not ultra high resolution knowledge, you're better off using X-rays. You're better off going to the XFM beam line, the SRX beam line at NSLS2, and probably doing the tomography, you know, like the chemical tomography that you learned about from, that was Ming who taught us. Yeah, Ming Yuan taught us that, right? So Ming Yuan was the one who taught about doing X-ray fluorescence and tomography. That might be the better approach if you're looking at something big. But if instead what you're thinking is, I've got this soil sample and I'm really interested in what's happening at the outermost region for some reason, what you might do is take that sample, embed it in your resin, use the fib or some other preparation technique to thin it down so that you had that local region, and then you could look at that either tomographically or just with standard transmission modes to try to characterize that. So Renee, was that a sufficient answer for you? Hopefully. Okay. Any other questions? Yeah, he said, yes, thank you. Okay, good. And a smiley face, lovely. There's a lot of material here, for sure, right? And as I mentioned, this is a class that I teach 29 lectures on each spring semester. If what you find is that, you know, I think these lectures are recorded, you can listen again, but also one of the things that I have done that may be of interest, if you find this an interesting and useful topic for you, is that I have actually posted all 29 of my lectures at nanohub.org. And so I'm just going to write that real quick to everyone. So if you go to www.nanohub.org, this is a site sponsored at Purdue where I used to work. Oh, and I misspelled it. There's only one N in nano. Nanohub.org. You can search for my name or search for transmission electron microscopy, and there's a full 29 lectures there. And again, if you know, really all you need to know is about EDS. I've got 2 lectures on inelastic scattering and EDS. There's another 2 lectures on eels, 3 lectures on STEM and the like. So I just wanted to offer that as a follow-up for you to learn more. Okay. More questions, I hope? No? Oh, come on. Anyone? Anyone? Okay. Well, Sal, what do we think?
So yeah, if there's no more questions, we could call it a day. Thank you very much.
You know, one of the things that's nice is actually I think we all recognize that tomorrow is Thanksgiving, so it's probably okay to take it a little easy. So good. Again, if you need any additional information, always feel free to contact me. The main lesson is that these capabilities are present for you to access at BNL. And if you need more information, feel free to look at those lectures online or contact me at any point. I often get people contacting me later from these lectures, and I'm always welcome. Always welcome it, and happy to talk with you about it. Okay.
All right. So with that, we'll call it a day, and thank you very much for attending. And for those of you in the United States,
no, I'm sorry. So I do now that I see there's this Q&A. There's 2 quick ones that I think I'm going to do real quick. So Tony asked, width of view meaning field of view. Just to clarify, you can go as low as 50 times magnification and as high as 15 million. So the field of view is highly variable just depending on the magnification that you choose. So you can look at things, microns wide, and you go to things at the angstrom scale. And then EC also asked, how does TEM compare to AFM? TEM's a transmission mode, AFM's a surface spectrum, surface mode, and the AFM, all you're doing is looking at surface topography. And I say all, it's useful, but it gives you no information about crystallography, defects, really, chemistry, things like that. So that's, I think, a main difference. So, great. Okay, so hopefully those were final answers. Now, Sal, you can go ahead. Sorry, I just happened to catch those over in the Q&A.
no, that's good.
I'm happy to take any questions.
Yeah. All right, so I guess if there are no more questions, we could just call it a day.
Call it a day.
And thank you very much. Really appreciate it.
Stay safe, everyone. It's a difficult time around the country, so stay safe, stay with your family, and don't travel, and be good, okay?
All right.